This evening is a special evening because we have really an internal person. So if you come here, maybe also the people online can see you. Philippe Bijlenga is a neurosurgeon here in HUG. And in particular, he is a neurovascular neurosurgeon. So he has a great expertise, also recognized internationally with the characterization and the treatment, of course, but the characterization that is not trivial of aneurysm. Aneurysm, I said correctly, yes. And why modelization? Because since the beginning he understood that is important for this pathology, for him and as for other pathologies, that to prevent the rupture of aneurysm, it's important to have a model that goes behind the, take into account the physical properties, the chemical properties, and it's for this that also he started to develop also modelization. He started also to be involved in what is important when you share data and how is important that these data are structured. And I asked him to spend the majority of his talk on this because it's important. He is also the referent for an initiative, European and with the Switzerland that is associated, that intends to find standardization for all type of data that are in neuroscience. So if you want, this is the presentation of the project, and as you can already imagine, we will follow up then to understand with you what are your needs, what are your kind of data, in a way that the European and then international community can profit and we can profit for the consortium. So thank you very much, Philippe, and go ahead.
So I'm bringing the microphone a little bit closer because it seems that I caught a cold yesterday in the airplane. So my voice is a little bit different than my usual voice. So yes, I will talk about data sharing in the advancement of science in general and in advancement of neuroscience more in particular. We'll give some examples and some perspectives. For those who are experts in the field of data sharing, I may do some shortcuts and I may do some simplification, and I'll always try to keep the essence of whatever concept which is behind, but maybe some might be offended by some obvious or too short shortcuts. So today we will talk about the purpose of data sharing. We'll talk about the challenges associated with data sharing. We will also talk about opportunities, perspectives, and finally, I will give my recommendation regarding practical consideration that can apply right now to everyone here. So I must say that science is now taking great benefit and will take great benefit of the vision of Tim Berners-Lee in the 70s. So just a little history about Tim Berners-Lee. Tim Berners-Lee is the child of two computer scientists, both involved in the building of the first sold computer. So he got very quickly this idea to use numbers to organize things. And you will see how actually he thought about a great vision. And the idea is that actually you can summarize very shortly life and your life in a triangle where you have the world, and between you and the world, what you try to optimize is your life, which is your interaction with the world. And well, you means that you're looking to optimize your liberty, but the world is very quickly gonna remind you that you should be responsible because you're interacting with the world. And what you try to keep is your autonomy, not having the world top on you and deciding everything for you. And that's quite a very important social discussion. So now, what about your data? You have data about you, and you have data you produce. And that is interacting with the data of the world. And what you want in your everyday life is combine your data, representing you, interacting with the world to optimize your decision-making and make better decisions. And that you can do it as an individual, you can do it as a teacher, as a researcher, as a professional, as an academician, or as a politician. And what changes when you go up here is that actually you need to be more and more accountable about the decision you take and about what you do. And if you mirror it, accountability is actually associated with transparency. And there are a lot of people, a lot of Nobel Prizes in economy that actually say that our world would be much better if it was much more transparent. And actually, if you have accountability and transparency, then you actually have an ability to have a real democracy. And actually, that's empowering people. And that's the old vision of the internet, a free internet, knowledge accessible for everyone, ever and every time. So now, if we look at what it empowered already, I must say that it's quite magnificent. Not so long ago, we had no maps, or we had very poor maps, and it was very difficult to acquire a position to know where we were on the globe. And nowadays, anyone can just with his iPhone, just interrogate and know precisely anytime where he is, what's the weather projection about the next days. Even you can extrapolate your trajectories and you can optimize the routes you're going to take according to traffic in real time. So regarding geography, we already benefit a lot from the internet. Now the issue when we interact with the system is autonomy. And we lost quite a lot about our autonomy already with the GAFA. Because what is going on now is a lot of people agreed to share very private data with Facebook, Google or Amazon regarding your taste, your interest. And currently the data is owned by those companies, which empowered them a lot because what they do is they actually push you information constantly about what you would like to have. So you're not deciding on what you want, they're deciding what you may like, and they're pushing you all the time information, so you lose your autonomy. They're pushing you to consume. So the idea, and that's a very new concept, and when I say very new, about what I'm gonna talk to you today, everything started in the 70s, 80s, and most of it is already online as guidelines for the last 20 years, but that is online and is working for the last 5 years. This came just with COVID. So the idea is actually to create what we call personal data stores, pods. And the idea is that actually we have protocols that allow us to manage our personal data. So we actually retrieve the data from all those companies and we maintain and manage our pods. And that's the latest idea of Tim Berners-Lee. And he came up with the SOLID protocol, and he is actively promoting industries to actually provide people the ability to have pods. And he himself created Inrupt, a company, which is a non-profit organization benefiting of the World Wide Web Consortium money to actually provide the ability that we as person can enjoy our autonomy much more than we do currently. That will have an impact on our health data too, but currently it's not adopted and currently it's not yet a reality. The other challenge is regarding information. What is information? Currently, most of the information on the internet is PDFs. And a PDF is actually very nice to look at, but the information in a PDF is completely lost. The text are just lines, there is no phrases. So to extract, you actually need to get it transformed to an image, and then you need to read it with an OCR, an automatic character recognition, and you need to rebuild the whole text. So it's a nightmare. So there is now a great aim and a great pushing from institution governments to actually get us, all of us, moving towards other formats of keeping data. So everybody uses Excel, which is better because you have matrices with data, but it's still very poor because Excel transforms the data and it's not interpretable. CSV is more interpretable, but it's still a format which is, everyone has a CSV with a different format. It's not universal. The idea is that whatever quantity we measure uses a unique identifier, so that actually we end up in every table to have the first line of the table defining all the columns with the same attributes, the same labels, so that actually when we share data, we automatically know when we talk about the same thing. So that's the idea of the RDF. The RDF is a new way to store data where you actually store it not in database, but in data stores, which means that actually you have a big bag and you just push the data in with tags. And that makes it much more easy. And the other thing is that it would be great if all the data stores were interconnected and interoperable. So we would have open data, linked open data. And that's more or less the magic word where everybody is pushing towards, that actually is going to represent all the human knowledge. So the idea can be summarized in 4 letters: make our data fair, which means findable, accessible, interoperable, and reusable. And most of people that ask for funding already know that you cannot ask any funding if you don't commit your data to be fair. So encoding knowledge is a very long and difficult task. The way we do it is we allocate a unique identifier on any kind of new concept. So if somebody discovers a new concept, he defines it, he published the definitions, and there are a repository where you have definitions, the concepts, and then you have the unique identifier that allows computers to know what you're talking about. And a unique identifier is a number. And as the universe of reals is infinite, there are an infinite number of numbers that can represent everything. And then what happens is that when you're a mathematician, what you do is you put things in relation with very simple functions. So you have one object, x, and you have another object, y, and you put those two objects, if they're in relation according to a function. So you can summarize the bounding of all the knowledges as relationships, y equal function of x. And what you do is you call x a subject, and you can y is the object. So you have one object, which is the one which is of interest. You call it the subject. And the other objects which are in relation with your subject are objects. And what we do when we talk is exactly that. We have the subject of a sentence. We have the relation with objects committed with the verbs in between. So a sentence is subject, verb, complement, or subject, verb, object. And you can put that into a formula, and that's the essence of the web of data. So that's the graph provided by the consortium, the World Wide Web Consortium, which organizes all those different blocks. So the first block you have, Unicode, is actually all the unique identifier is the number that defines all the letters. And there are about 6,000 or 7,000 different ways to have characters. And if we put the Chinese characters, we can increase even more. So there's a lot of work to actually give a unique identifier on all the characters that the humans invented ever. So that's the work of the Unicode. So there are people, their whole life, what they do is find new characters and encode it, define it, and give a unique identifier to those characters. And then mathematicians, they love using characters nobody uses to characterize a new thing. Then what you can do is you can actually give a unique identifier of anything by adding those codes. So for example, the sun, S-U-N, you can label it the sun, and you're going to have a number which is a combination of the Unicode of S, U, and N. And this is the unique identifier for a computer regarding the sun. So if you define it, the computer, when you will see S-U-N, will understand you're talking about something in the sky. Then you can organize the things with semantic. And then you have a protocol that allows you to organize sentences in a text, which a computer understands, and this is the XML protocol. And when you have a resource description frame, that's something we are, as I mentioned, working on, and you will see, is actually representing the knowledge we have, the relationship we know about the things that are interconnected. So that's a graph that defines all the connections we know already about the things we're experimenting. And then you can have that under a schema, and then there is a language, the Sparkle, that actually allow you to query and to make association and ask computers to look for data regarding whatever concept you want to be associated, or you want to check if it's associated or not with another concept. And you can even ask that it quantifies the relationships. And this all ends up to the possibility to write codes that are actually applications which allow users to interact with the data and get answers all the time on everyday questions. So actually, when you're asking where you are on Earth with your iPhone, you have a Sparkle query that is looking at your actual position and is requesting to have all the map of the globe and everything you want associated with it, and then it designs it on Google, and you can see it on your iPhone. So what we have to do as scientists is go from tables where we have columns that actually allow us to define all the different objects we're looking at, and then all the lines with all the experiments we do, transformed into relational databases when we do multiple experiments that are in relation with each other, which was what we did 10 years ago, 5 years ago, to now triple stores. And the triple stores is a name for those XML files, which now have a name .json, JSON. So we don't have .txt, we now have .json, which is the format we're going to use to actually keep our data and store our data in data stores. So now, to make it possible, we're not experts as clinicians, researchers, we're not experts in that. We need to have IT people helping us. And we're lucky in Switzerland that there has been an initiative where they try to connect all the hospitals together with the Swiss Personalized Health Network. So what they saw is that all hospitals had data, a lot of data, but in a very heterogeneous format. And the idea was actually to homogenize all that. And actually people were aware about what Tim Berners was thinking about the W3C recommendation. So they adopted very early the idea of performing and doing RDF stores and having a knowledge graph here on the right left where actually we can interact with. But that requires what we call schema forge and to have some standards and terminology services. And who best than us, specialists, which are experimented in the domain, to define what are the relevant concepts, what are the good definitions, what are the categories that define correctly an entity. So that work is currently in process. It's progressing. It's very heavy, lots of work, but every project now should be participating to its effort in the domain of competency. And this happens in Switzerland with the HPHN, but happens also in the United States with the common data elements libraries that the NIH is promoting and the NINDS is promoting too. And similarly to the SPHN infrastructure, there is the SETR infrastructure in the States. And I really advise you to read this Nature scientific data paper that came last year from our Swiss Personalized Health Network team about the verification of health-related data using semantic web technologies. So actually we can be quite proud in Switzerland. We have an infrastructure and we have people that actually were able to publish in Nature Medicine, an innovative concept which is applied in the real world. So there's a lot of work for us in the biology, medical, and clinical world, because the fact we're talking about people made that we didn't progress much because we were afraid regarding data privacy, and we're not so accounted with IT. So we're quite behind, because if you look on the internet on a website called lodcloud.net, you will see that that's the summary. It's kind of a visualization of all the data which is connected on the internet right now. It's in real time. So it looks like this. And that's not the data. This is the map of all the interlinked data repository we have. And you will see that in the center, there's something called the DBpedia. So that's the register which registers all the data stores. And then you will see here that there is Wikidata. That's something that describes all the data. And on top of Wikidata, to make the human beings understanding what the data is, what do you think you have? Everybody knows, everybody used Wikipedia. So the architecture is built that we interface with Wikipedia, which is interfacing with Wikidata, which is interfacing with DB data, which allows to describe all the data which is there. So now you're going to have all the different colors, and all the different colors are actually to describe what is about economy, what is about geography, what is about literature, and in red, what is about biology. And actually, if we look carefully into it, medicine is one dot. Standard nomenclature in medicine, SNOMED clinical terms. That's the registry of what doctors believe are essential elements describing human beings that need to be treated. So what is represented here? ICD codes and jobs, interventions. And that's only for billing. There is very little about the essential concepts of medicine there, because researchers were reluctant to actually introduce the data or share the data. So actually this is so far only built by administrator for administrating and billing. It's sad. So the reason is mainly because there needs trust. And we have laws already. We have the GDPR, which very clearly defined what is data protection and how data should be stored, maintained, monitored, protected. On the other side, when we work on a tool which is universal, we need to have data which represents a reality. If we want to have good models, we need to have a good representation of reality. If the reality is distorted, then the models are distorted and doesn't represent reality. So there we have good practices. And good practices are recommendations because we cannot do more than recommend people to work well. But there's a checklist and there's a method on how we should perform research to actually minimize the risk that we have biases or that we have wrong conclusions. So actually to get everyone sharing knowledge and benefiting of the data, we need that data to be protected and stored. And right now, as long as people are not empowered to the use of their data and we don't have pods, we, as people responsible in hospitals, doctors, or institutions, or even governments are responsible to protect vulnerable people. And therefore, we need to keep our data protected. And that's a schema which is actually from 2014 and is the basis of the work regarding how we store the data and we manage the flow of data to actually protect the data. So the data is acquired anyway in hospitals. We cannot work without data in a hospital. But the hospital is protected behind a firewall, and some people have the duty to keep that wall very high and to make it very difficult for people to cross the wall. But we saw that, sadly, people are able to actually get in, store the data, and then ask for money. So it's our duty to keep the data safe in the hospitals. And no one is accessing that data in the hospitals. What we can do is we can filter the data out for a specific purpose to decrease the amount of data which is exposed and actually store that data in a place we call the non-care zone under the responsibility of a TTP. What is a TTP? It's a third trusted party. It's somebody who is responsible to keep the data safe. And on top of that TTP, you have an office, an operation office. And that operation office is somebody who's actually making the coordinating between the care zone and the research zone. That's a manager who is making so that actually people can know what is coming in and know what is going out and for what things are going out. And in the middle here, you're going to have the filter. And here, what we have in Switzerland is the SPHN connector. Now, if you as a researcher, you say, well, I have an idea. I want to have access to the data. How can you do? Well, the first thing, we need to check your idea is original or useful. We need to check that you actually have the resources to do it and the competencies to do it. Because if you're not competent to do it, why should we give access? So actually you don't achieve a result. So there is an IRB and an IEC. IRB is an institutional review research board, and an IEC is an institutional ethic commission, which is actually checking that before we start using the data, we actually have a good plan and all the means to perform what we want. And then there should be actually a scientific advisory board to help things to be running smoothly. And there's this idea from the European Commission that whenever you extract data, whenever you take a data set and you push it out of the non-care zone, it should not be identifiable. No one should be identifiable. So if you have a request that ends up with a single patient, it means that you're able to identify the patient because there's only one patient that have the characteristics you're asking for. So actually, if you have only one patient, it means that you have a privacy breach. So the idea is that in the system, when you make a request, it should be checked the number of patients that are coming. And if there is less than 7 patients, the system should not provide any data. And if 7 is because it's the smallest number where you can start to do some statistics. The other idea which is coming up is that actually, sooner or later, we will not need to produce data sets we export to people. We actually can produce what we call mock data set. It's a representation of, it's an artificial representation of the data, which allows to actually reasonably code the analysis you want to do or build the application you want to build. And once you finally have a final tool and it works well, you can send it to the RAB and IRC, and if they accept, they actually get the operation office running the data on the raw data directly and give you back the aggregated data. So actually the data is never traveling out. And that's a very safe way to do. And finally, the latest concepts from a few years ago is to actually produce synthetic data. We're actually able, theoretically, to produce an artificial data set that perfectly represents the original data set, but has any patient which is real. And that's the best way actually to work, because you can send that out without having any risk of having a privacy breach. And synthetic data is very interesting because you can actually demultiply. So if you have a cohort of 100 patients, you can suddenly produce a cohort of 10,000 patients because you actually do 10 or 100 replicates, synthetic data replicates of the original one, and it amplifies the numbers. Finally, when you finish all your studies, you might have new innovations, discoveries, which are going to be implemented back in the care zone with new recommendations, with new tools to assess patients, which will bring new data in you can use later on. So that's kind of a circle where things improve iteratively. So now I'm going to share a little bit my experience. I was, as in the introduction, working mainly on aneurysms. And aneurysm is a complex disease because it has multiple stages. It's a multifactorial disease, which we really struggle for quite a while, the international community, on understanding and actually being able to have clinically usable scores or tools to make some prediction and take decisions. So the idea was that actually in 2004, consortia around the globe decided to adopt an unbiased approach, taking the most initial conditions we can have, looking at the genomes of people. So the idea was actually to get genomes of all the people that were diagnosed with aneurysms over a certain period and over a certain area, and then to pool all that data. And around 2009, 2010, we came up with the first genetic GWAS study on intracranial aneurysm, looking and finding that there were 3 genes that were clearly associated with the disease. Those 3 genes were actually 3 loci, and we couldn't understand what it meant, but we had actually 3 biomarkers. Then we continued, and now, 2020, we came out with 17 new loci. And we start here to have some loci which are associated with drug targets, with some pathological mechanisms. So suddenly we try to find out in the genome that there are a few things that correspond to what we know. Then we look at the phenotypes of all those patients, because when we acquired the genotypes, we also acquired genotypes at the same time about these patients to characterize them. And actually we looked at all the different factors we are interested in, and we were able to characterize distributions. But we saw that the interaction between factors were very complex. There was nothing linear. There were lots of interactions between factors. And that's where we came up with a phenotype-genotype score, which actually was very deceiving, because the area under the curve, the ability to predict really if people had an aneurysm or not, if the aneurysm were ruptured or not at diagnosis, was around 60%. Well, 60% is rather poor if you want to take a decision. So we learned a lot, but we understood that that was not the good way to go. So what we did is that we started thinking about probabilistic views, and we looked into more advanced way of doing statistics, and that's where we actually really applied Bayesian statistics. And I will not come back to Bayesian theorem now, I did it already previously, but the idea is that you can have a graph using the Bayesian theorem, using the mathematics which is behind, which actually shows the links you have between the different factors, and it demonstrates the interactions, and actually it allows you to have to be more precise and actually give better predictions. Now, with the number of cases we have, we're still not powered enough to give a clear picture. So we went from 6,000 cases and 14,000 controls to almost 39,000 cases and more than 2,600,000 controls. And with that data, we hope that we will be able to go looking at difference between genders and looking at cellular specific targets to actually understand the cellular mechanisms of the disease on one side. And that's a study we're just starting now. And the other side, since December last year, we're starting the project Gemini, where we try to actually generate what we call a digital twin of aneurysm and of stroke. So actually here we're looking really very ambitiously to cover all stroke, ischemic stroke and hemorrhagic stroke, and specifically aneurysms. And here we're going to do heavy statistics and heavy modeling. I will come back to that right now. So Gemini will deliver a multi-organ and scale digital twin in health, a DTH. Remember DTH, which is something I will come back to it. This will improve understanding and support treatment selection for stroke and addressing both acute ischemic and hemorrhagic stroke. It covers the heart, the vessels, and the brain. And we start with data we receive from the clinics. So it will be HIS information system, hospital information system data. It will be imaging data we can extract from PACS, and it will be public data, meaning data we can extract from PubMed. And with that, we're going to start our knowledge graph. That we already did. We're going to look what are the association between patient, aneurysm morphology, genetics, and population data. And we will look how we can predict the transition of an aneurysm from one stage to the other using biomechanics. So what we're going to do is we're going to use the laws of physics and the laws of biology to building simulators, models, digital models that can, having the initial conditions, predict what will be the result after a certain amount of time, applying physics, so flow, shear stress, maps on the vessel wall, looking at the behavior of endothelial cells, responding to those shear stress or different injuries, and looking at the effect it will have on the blood clotting inside the aneurysm, and so on. And we will then, using those mathematical models, produce what we call quantities of interest that we will replace the current factors we use in clinic. So the factors we use in clinics are very roughly assessed, and they are very roughly categorized with a very low granularity. And if we have models, we're going to produce numbers in a much more precise way and much closer to the principal factors that are involved in the disease itself. And then we will look at adding treatments, because all the patients we treat actually hide the progression, the natural history of the disease. All patients we treated, we're not able to follow them and know what the natural disease will be. And we cannot ethically let the disease progress. So we need to have the treatment to actually compensate the bias induced by treatment. And then we will add also, and that's to get to the next step I will just discuss in a few seconds, which links to the brain. So we will be interested into the vasospasm period at the intensive care to actually show what happens when chronically the brain is hypoperfused, and see how it reacts on the EEG, how it reacts on the survival of neurons. So what we will do is we will use biomechanic modeling to actually have new quantities of interest, and we use Bayesian mathematics, Bayesian theorem, and Bayesian networks to actually model that and display it. So now, seen another way, that's the theory we're working on, is that we have a structure, a vessel wall, and this vessel wall is composed of endothelial cells, elastin, collagen, and smooth muscle. and we can actually look how those different entities are modified by the disease. And we can actually model how those are interacting according to an injury. And the injury is the pressure of the blood on the wall, is the friction of the blood on the wall. And we are actually modeling that interaction between the injury by the physics of the blood flow in the vessel with the structure. And we are going to have injuries, and every time we have an injury in the body, there is some repair. And we're going to model the repair mechanisms. We're going to look for factors that allow to understand how stem cells, inflammatory cells, and smooth muscle cells are reacting to that injury and how they recover the tissue. So that's the hypothesis we're working on, is that's what we're going to simulate biomechanically in the models. Now, the other thing is that we assume that there is some random events. When you walk in a city, you have a risk to have a car injury. If you're blind and you walk in the city, your risk you have a car accident are much higher. But we cannot say for sure that all blind people will have a car accident on a certain day. So what we assume is that all our models will allow having probabilities, higher or lower probabilities to be exposed to an injury. And that we're going to model with what we call the Swiss cheese model. And the idea is that we have different types of filters: genetic predisposition, congenital predisposition, environmental factors, and modifiable factors, which might be drugs or treatments. Some are permanent, some are changing. And so we can identify the holes, and if the triggers happen at a certain time and there are holes aligned, we have an aneurysm rupture. And that model is very well known in industry. And there are mathematical models that actually model that very well. So what we're going to do is we're not going to reinvent the wheel. So we will just reuse what has been done already and apply it to the field. So how does it look like? That's the latest model, which is predicting, according to the factors we know, the probability of a patient to be diagnosed with a rupture or an unruptured aneurysm. And what you see here is that you have distributions and you have arrows between the factors, and you see that there are things that are interacting. Now, this is a dynamic display, because now what I can do is I can fix a factor, and I know that I'm faced to a woman. So I can actually remove all the males, and then I have a vision of the probability distributions of all those different factors according to the gender, female and then male. And you can see that here, there are some differences between male and females. And you see that the differences are mainly in location and smoking. But location and smoking are two factors that have an effect on aneurysm rupture. Is it a synergy? Is it going against one of another? So that's what we're going to look at. So what we're going to do then is add factors regarding interventions to remove the bias induced by the fact that we don't know what's going to happen on aneurysm that are treated. And we look at mortality, because at the end, what we're interested in is disability of the patient. So we're going to move adding mortality and disability, and that's what we're currently doing to the model. And then what we're going to do is replace. We're not going to add, as we always do as doctors, we always add new factors. No, what we're going to do is we're going to replace a poor factor by a better factor. A better factor means that we have a more quantitative factor, which is more reliable, which is measured automatically, very precisely. And aneurysm shape, we have very good indicators on aneurysm shape. So we will replace aneurysm size by aneurysm shape. And hypertension, what does it mean? Hypertension, responsive to treatment, non-responsive to treatment, not aware about and not treated. Well, what we're going to do is we're going to most probably look at cerebrovascular autoregulation. So we will get patients doing a test that assess their autoregulation ability. And that more probably is going to be a much better surrogate about the likelihood of having an injury or not. So we're going to replace those factors and maybe add one factor we really need. We have no information regarding the vessel wall. So what we will do is we will most probably have, and we're working on identifying a marker, a biomarker on the imaging on the vessel wall that allows us to know where we are. How healthy is the vessel wall, or how diseased is the vessel wall, to actually know and better classify the patients. And this will then end up in a model where we can experiment, take all and fix all the variables we know and project what are the most frequent operations or interventions done on those types of patients? And what are the results, the outcomes, the disabilities and the mortality associated with those different interventions? And that will hopefully allow us to make better prediction and take better decisions. So that's what we foresee as a very low granularity digital twin. You know, digital twin is actually something that is an idea that came from the Apollo 13 mission to the moon. The NASA, when they were going to the moon, very early understood that if anything happened on the moon, no engineer could go on the moon to check what and how they could fix the problem. So they had a real twin of the module on Earth. And whenever something happened on the moon, they were calling Earth, and on Earth would have hundreds of engineers working on the duplicate to actually find a solution. But what happens in space and what happens on Earth is not the same. So when you have a bucket of oxygen that explodes when you're traveling from the moon back to the Earth in the vacuum, how can you simulate that on Earth in the 60s? Very difficult in the 70s. Very difficult. So that's why they actually took a digital replicate instead of a real replicate, and they digitally transformed the environment to match the space vacuum. And that's why they thought about the digital twin, and that's where they set up all the conditions on how to build a digital twin of something. So now we're working on, and this is again a European project that is funded, which is running now, which is covering the building of an ecosystem, a roadmap, a repository of data, and simulation platforms to actually allow to have digital twins in human physiology. Now, if you have digital twins, what you can start to do and think about is doing in silico trials, meaning that you run clinical trials on virtual patients. And it has been done already for liver. The liver, the chemistry of the liver is very well known. And you actually can very well know how a drug will be modified by the liver. And you can predict the molecules that will come out of a liver of any individual on a computer. And then you can check it in the reality. But if you precisely know what you want, you don't need to make such a big study. You just need to make a validation study. So the FDA is looking at that, and they are, again, writing guidelines, regulations on how to do it. And now they said here, in silico clinical trials have a range of possible applications, including but not limited to augmenting or reducing the size of a real-world clinical trial, providing improved inclusion-exclusion criteria, or investigating a device safety concern for which a real-world clinical trial would be unethical. So that opens a lot of avenue for us, because we expose our patients to a lot of treatment that, if not performed, are life-threatening. So whatever new device we want to test, we may have the opportunity to test it first in silico before we expose patients to risks. So that allows to give you a little bit of history regarding the idea of Marco Viceconti and Peter Hunter in, I would say, the 90s. One in Bologna, the other one in New Zealand and Auckland, to actually think big and think about what they call the virtual physiological human. So Marco Viceconti is an engineer, Peter Hunter is a physiologist, and those two collaborated to actually make that vision true. Now, that's all about physiology. We, neuroscientists, neurosurgeons, we're interested in the brain. And we would like to have our iPhone, Google, whatever, for interacting with our patients regarding physiology of the body and the brain function. So that's the list about all the currently funded flagships projects of the European Commission. And they very clearly asked us to collaborate. So we have 4 years to find ways to make bridges between those projects and come up with more than what we actually committed in the project we submitted. So Gemini and Target are 2 projects on strokes. So that's clear that Gemini and Targets, we have to collaborate, and we will collaborate. Vital is about a virtual twin for personalized clinical care. Wow, great. We're very interested. So we are most probably going to do an extension and try to collaborate with Vital. And on the other side, Well, there's the virtual brain twin. And that's a very interesting project we'd like to bridge too. It's on psychiatric disorders. And well, it's very interesting to know what's going on about psychiatric disorders in patients with stroke. So we're definitely going to bridge with them too. Now, that's a bit difficult because physiology and brain, they were progressing on two different funding routes, and they were siloed, and there is not much interactions between the two groups. It's only now that we're starting to interact. So we have data sets, and data sets are here represented with those graphs coming from different diseases, different centers, and we need to synchronize those data sets. And what we try is to have a reference. We know from our knowledge that actually align all the concepts from the literature. And what we do is we can actually align those data on the map, and then we can merge them together to actually do what we call a multi-center, multi-disease study, and have a representation of knowledge that integrates all that. But then what happens if we have two domains which are not connected? Well, what we can do is actually find out what are the two dimensions, the two objects that are more likely to be connected, and run a study to look for that. And that's regarding the physiology and the brain. We know that there is something at the interface which is called the cerebrovascular unit. And we're going to build a study to actually do that link that bridges those two domains. And well, if we look on the brain side, there has been a lot of initiatives to actually do brain mapping, brain function mapping. So we have a lot of atlases, but all those atlases are not really communicating between them. So we are in Europe, and the issue is that all those different projects had a problem that it was top down. And now the idea is to change the philosophy and to do it bottom up, meaning that what we're going to supply is infrastructures to the scientists to be able to work in what we called a sandbox, a safe sandbox. So we are going to create an environment for researchers where they can actually freely work, being protected from all the issues and all the administration associated with research. So there's the eBrain project, which is actually the new name for what was previously the Human Brain Project. And they have a platform which is highly funded by the EU and by the Swiss government, where they allow you to actually store your data, to say if you agree to share your data, to create brain atlases, deliver, test, and share modeling, simulations, and computing power, allow infrastructure to actually validate your hypothesis or make inferences, and create a real health research platform across Europe regarding patients. And that's where it's very interesting also, because that happens in Lausanne with Philippe Rivelin, who actually is the father of the medical information platform, where it's a disease-oriented federation of different infrastructure on dementia, traumatic brain injury, mental health, and epilepsy. And it has been funded very recently by the European community and by CERI in Switzerland. So that's a platform which is funded, which will grow. And as I always say, if you participate in the building of something, you make it a little bit yours. It fits better your use. So I highly recommend to be involved in those projects, which are funded by producing and submitting your own results to that platform. You can actually send it to other platforms, but that's the official platform around in Switzerland and in Europe. Now, as you know, politically, Europe is a federation of states. Switzerland is not part of Europe, so it's an independent state. So what happened is that actually they decided that there would be state nodes that will manage locally whatever happens regarding eBrain, and that will all be federated. So there are national nodes. They are representative of the national node, and we are looking for a Swiss representative. Well, we have discussions, and we actually defined a mission specific to the Swiss node, which is actually provide a competitive advantage, and that by providing resources for data storage, data sharing, modeling, machine learning, simulation, computing infrastructure, and health research platforms. So people are working to make a sandbox so you can play. There is some administration, so we're thinking and still discussing on how it will be more or less governed. That's always necessary, but what we know is that the Swiss universities and institutions, the biotechs, Swiss Specialized Health Network, and the Swiss Federation of Clinical Neuroscience Societies committed actually to work on that platform. And it's funded by the CERI, It's funded by the Swiss National Fund, and it will be funded by the Swiss universities and companies. Currently, what we're doing is we're doing an inventory. I'm responsible to make the inventory in Geneva, and that's the reason today I'm talking to you, is actually to know who is interested, who is doing what, just to inform you that there's something going on. And then my duty is actually to come back with an inventory of potential interests, with an inventory of potential data and data volumes to be stored, archived. If people are keen or not to make that data available to the community, if they are keen or not to participate in the effort to make the data fair, to work on the data management plan. If people are interested in services, if there are specific services regarding things you see that are not available and that maybe people in Switzerland can offer. On the other side, do you have services that may interest people? Do you have any kind of models or whatever you want to show other people and you want to have other people validate? Or maybe you want to provide because you validated it and you think it's a useful tool. So that's important to know and that's important to share. Now, my recommendation is, you know now, when you work, when you ask for funding or when you publish, you need an archive. So you already have your own unique identifier. The institution have a unique identifier. The documents you're doing have a document identifier. So a lot of your work is already identifiable and identified. But it's not fair. And now funding agencies and publishers are asking you to actually put your data and your analysis codes on repositories on the open space. So there are general repositories like Zenodo, but if you look, Zenodo is not FAIR compliant. The Harvard Dataverse is FAIR compliant. The Figshare is FAIR compliant. So you should actually look for FAIR compliant repositories. Now, if you look at health sciences, you will see that there are other repositories. And if you look in neurosciences, there is Neuromorpho, Open Neuro, there's eBrains. Well, there's one here on the list, which is FAIR compliant. And what does it mean to be FAIR compliant? It means that whatever item you measure, you should have a look on SPHN to see if you find it, if you actually quantify it the way it's defined it should be, or transform your data to actually be compliant with the standards and provide not a CSV file, not an Excel file, but provide a JSON file, which actually puts a unique identifier associated with your measures and a triplet. And then that is pushed by SPHN on the data store. And then you have this nice figure where it applies to the knowledge and it's adding some information to the overall knowledge. The other thing and I don't know if everybody heard about it because it's quite recent. I discovered a few years ago, I think it was during COVID, that there are Gits. And Gits is actually softwares that allow to work on codes in teams and actually to have a control about tracking versions and working together. And you have GitHub, which is one of the services that allows and is really, I think, the most popular one, where you can actually code as a team and keep on tracking the versions of the files and take one version to apply it on a data set. And that code, when you publish, you can share it with your papers and with your data, which make your research completely transparent and completely reproducible. And your codes can be applied on other data sets, so people are going to validate your data. That's going to increase the power of your research a lot. So I really, really recommend that you do the effort to actually work that way. And finally, if those are doing complex models or models that may be actually integrated in the chain of models to actually model a whole system, you should actually read the VNV 40, which is the latest version, about how to write a code to get it interoperable so that actually can be introduced as a brick in a chain of bricks that builds a building of knowledge and eventually an application. And that's my last recommendation. Please don't work at home on your computer. Don't share your files using emails. Work in a safe space. Use safe data sharing. You might not understand the importance of it, but please do it. University is providing you a shared environment, And the European Commission and the Swiss SNF is working on improving. So actually, you have less and less to worry about doing the things correctly, being less exposed about privacy breach, being less exposed to unethical behavior. And actually, the optimum is that when you want to send your research project, you have to send a data management plan. The easiest would be actually to adhere to a structure and take their management plan. So in conclusion, science is a global human adventure to better understand everything forever and for everyone. Knowledge is a legacy for a future generation. And please generate your ID for whatever new concepts you discover. Make your data fair. Work in safe digital spaces. Code your models and share your models so that actually we can go from the anatomy to data, and from data to models, and from models to digital twins. Thank you very much.